Okay, first slide. The first thing I want to do is move a slide. So I'm just going to bring us back to this slide. In part one, towards the end of part one, I came unstuck on this plot down here, which I said was an SWR plot, and I couldn't get my head around it. I went back and looked at it. So this is a low-pass filter. It is comparatively well matched low down, and the SWR reading here is 1.2 to 1, and then when it becomes mismatched, that's what we see here in an SWR plot. And this little ding here in the S11 plot is that ding there. So that SWR plot is correct. I just couldn't get my head around it for some reason the other day. Okay, so, and David can edit that in and make me look all slick, right? Right, so this is what we did on Friday. We got down to touchstone data sets. We had about 5 slides to go and I got called time. So I'm a little bit lengthy on this session, so I'll have to go fairly quickly. We're going to start by continuing the explanation of S parameters, and then I'm going to demonstrate the product step by step, walk you through some of the demonstration stages that you need to go through, including an introduction to the whole demo kit, calibration files and certificates that come with the kit, connectors, test cables, and connecting the DUT. We need to look at the Smith chart yet. We haven't yet introduced what a Smith chart is, and the VNA is producing those, so we better understand what a Smith chart is. I'm going to show you how to demonstrate leading edge performance, because a lot of the times you use a VNA, you're not using it at the very best level of performance that can be achieved. But if you want to get to specification, as on the data sheet, then there are certain things you have to do to get right down to that level of performance. We will wholly characterize our DUT. Ta-da, our DUT. That we will come back to and wholly characterize. And then I'm going to talk about calibration and standards. And that's something we need to remember in our demonstrations. You're going to see that calibration is a fairly lengthy and slightly tedious process, as it is for any VNA, and not the thing that you start your pitch with. So this demonstration will all be based on files that I've pre-prepared for you, and then details of how to actually demonstrate a calibration, which you do later on. Then we can take a look at some advanced features and the competitive comparison. And at that point we'll call it a day, and we'll face the barrage of questions that haven't been answered by the whole presentation, I'm sure. And I'll take questions any time through as well. I don't mean to put them to the end. Right, so being a network analyzer, we want to measure the properties of a network. That's different from a scope. A scope measures signals that come out of a port or come out of a probe or whatever. They measure signals. But the end result from a network analyzer, as we saw in part one, is an analysis of a network. It processes signals that went into the network and signals that come out of the network. We saw the example of the network analyzer typically measuring ratio of an output wave to an input wave. I did that using a picoscope, and we gained the attenuation between them. We ratioed the output, the B wave, to the A wave, the input, and we achieved a gain plot. And that's what a scalar network analyzer does for us. So a network analyzer displays a result that is a mathematical operation on at least 2 measurements. And then puts that on the screen, not the signals themselves. Very important. Let's talk about scattering parameters. So let's talk about S parameters. I've got here a source, an electromagnetic wave. Quite bright, so we need to be careful not to shine it too much in the camera there. This might look like a vacuum cleaner tube, but in fact it's a transmission line. We're going to pass the electromagnetic wave through the tube, through the transmission line, constraining the electromagnetic wave within the line. Might look like a balloon, but that's a dot. And if we were to pass the electromagnetic wave into the dot, we'd see a transmitted wave coming through the dot. And you might see that's towards a pinkish colour. In other words, from a source of white light, we have selected pink as a band of frequencies. So, like I say, you might think of it as a balloon, but let's try and think of it as a bandpass filter for the electromagnetic wave that is being applied to one port and emerging from another port. You might also be able to see, if I turn around this way, that there's a considerable amount of light reflecting off the dot. It's kind of white, it's got a hint of pink, but it's a kind of, it's mainly white light, I would say, coming off the surface there. And so the electromagnetic wave is hitting the dot. A lot of the wave is reflecting from the dot, and some is passing through the dot. And you might be able to see here that actually there's a little bit of electromagnetic wave emerging from all over the dot. In other words, you can think of this particular one dot as having an infinite number of ports all the way around it. The electromagnetic wave is scattering. It's scattering off the surface of the dot, and it's scattering as it passes through the dot, out of its walls, and it's scattering to atmosphere, or the ether actually, I suppose. It's scattering as it leaves the dot. So, balloon. Let's put that one down, and let's get ourselves a two-port dot. An input port and an output port, and that might look like a balloon stretched over the end, but let's think of it as our bandpass filter. And now we're selecting a yellow light from our white spectrum. Let me get another dot. Here's another two-port dot. This one, let's put some electromagnetic wave through it. That's an orange dot. Port 1, port 2, orange light. It's an orange bandpass filter. Now, if we were to connect the two dots together and we pass the electromagnetic wave through both of them, we can perhaps begin to imagine what's going on here. We can imagine that the white light is bouncing off the yellow dot. The yellow dot is reflecting some light back and passing some yellow light forward to the orange dot. And then some of the light, and it's a very small amount actually now, there's a little bit of light, of electromagnetic wave emerging from our port 2 in the now system. But there's a lot of complicated stuff going on in here, because off the orange dot we've also seen a reflection back. That'll be back to the yellow dot, then it'll reflect off the yellow dot and come back out of the orange port. Some of it goes back through the yellow dot, comes back to the source, and being a light with a reflector at the back. That is a very good reflecting source, and so the light coming back along here will be reflecting back forward again, passing back through. It's already passed through the orange, or passed through the yellow, bounced off the orange, gone back through the yellow. Now it's going through the yellow again. You might imagine that it's quite complicated to work out exactly what frequencies are emerging from port 2 of the system because of all the reflections going on internally. And so what S parameters do for us is they describe that reflected light and the transmitted light off each dot, and we can couple the S parameters together mathematically, and those S parameters will allow us to figure out exactly what emerges from our now fully characterized network. The whole thing is, if you like, we can depict the balloon like this. Here's the transmitted wave. It was basically white. We had some sort of orange whitish reflection. We had an orange transmission through, orange transmission out. We probably had internal reflections as well. Oops, I'm sorry. Just blinded two of the audience at least. We can see the reflection going on. This is a reflection from, this is a reflection back out of here, and scattering all over the place. If I put the two dots together, and the diagrams describe what I've just done, you can see that it really is quite complicated to even begin to think about and work out what the final colour and intensity will be. And this is just an electromagnetic wave in a transmission line. And the whole thing applies to any electromagnetic wave in any constrained transmission line. A coax cable is obviously constrained. It's got this big shield around it, hasn't it? And the microwaves are contained within. Transmission lines on PCBs, it's not so obvious that things are constrained, but they actually are, because microwaves traveling in a transmission line on a board, although you can see the transmission line, fields around the flow are constraining things to the, not the conductor actually, to the board material itself. So the electromagnetic wave travels across the board and is constrained within the board, and not much escapes. And this goes on at any frequency. So if we knew how each frequency of light scattered back off the dot and through the dot, we would know what light goes forward to the next dot. So we need to know the extent of transmission and reflection at every frequency of light. Quite high frequencies, of course, but the same applies. Now, this is what scattering parameters are all about. And I believe actually that this is the origin of scattering parameters, but I'm not absolutely sure of it. So if I'm wrong there, just remember what scattering parameters are from the demo. So this is the diagram that we alluded to right at the beginning of the part 1 presentation the other day. This diagram sits on the front of the VNA. It's always there to remind us of what the scattering parameters are and how they relate to the ports. So here's the explanation of them. The S11 describes the signal coming out of port 1 as a result of the signal on port 1. Not the total signal coming out of port 1, but the signal out of port 1 as a result of the incident wave on port 1. And we said the other day, the A wave is going to be the incident wave, a vector quantity that we talked about, and B wave is going to be the return signal. But S11 relates the A wave going in, coming out to the A wave going in. And this carries on right through. S21 is the transmitted wave from port 2 as a result of the incident wave on port 1. And here, the wave out of port 2 as a result of the wave on port 2, incident to port 2. And so on and so forth. The S12 relates the wave coming out of port 1 due to the wave on port 2. And if you know the behavior of the electromagnetic waves of any frequency whatsoever through the scattering parameters, you have characterized that device well enough to put the devices together in a system and predict performance. It's crunchy maths, but you can do it.
Just a quick, should the A and the B be the other way around on the right hand side?
Should the A and the B... Ooh! You're right. You're absolutely right. Can we... have we got gold stars? You've got croissants. You're absolutely right. Yes, that's a copy and paste error, isn't it? This is the B wave coming out, and this is the A wave going on. Thank you very much. Thank you. We'll get that corrected. That shows we're all attending. That's good. Or attentive. Right. Now, as it happens, the way things are calculated out here, the S11 is the ratio of the B wave and the A wave. These are vector quantities. So if you remember, the things that come off our receivers are vectors. Or vector numbers. So this is a vector division, S21. So this is B divided by A. It's basically gain, like in the scalar network analyzer. And this is basically gain. Actually, it's an attenuation. There's an amount of the signal, if you like, that comes back off the port when a signal hits the port. So all the S parameters are vector manipulations of the A wave and the B wave coming off the receivers. And S parameters are, of course, vector quantities in themselves as a result of that. So the vector network analyzer finds these quantities in forward and reverse measurements, and it does that first and foremost, and then it calculates lots of other things, but it has to do that vector maths first, just as the scalar network analyzer does scalar maths first. Now, the whole thing, S parameters can expand to as many ports as you like. You could have S parameters describing the entire behavior of that balloon. It'd be an absolute living nightmare, but you could. I've drawn here a 3-port. So if I have 3 ports on a device, then there's a relationship between every one of the ports. And it was Hewlett-Packard many years ago saw the S parameters as the way forward for analyzing microwave components. They focused all their products on S parameters. You can have many forms of parameters defining electromagnetic wave behavior. You can have other forms. They're all calculable from one another. But S parameters are really the ones that allow you to combine multiple units together and conclude a result. Easiest. And they defined a standard format for S parameters. They were called the touchstone format. And they have the file extensions when they're saved as .s1p, s2p, s3p, etc. S1P is for a single port device and has one vector set. S2P has 4 vector sets. It describes the behavior of 2 ports. S3P has 9 vector sets, and so on and so forth. The number of ports carries to the square in the number of data sets that you're going to need to describe behavior of that device. Touchstone, as you'll see in a minute, basically a tab-separated data file. CSV and text forms are used by various people, but the Touchstone format is tab-separated data. And the importance, as I've already said, of S parameters is that once I know them, I can cascade them in a system and describe an entire system. So I could have S parameters for a coax cable and S parameters for a connector and describe how the two work together. And most microwave manufacturers give S parameters for the components that they make, whether they're amplifiers, transistors, cables, connectors, couplers. They're all described in terms of specification in S parameter files. Not written out in longhand in your data sheet, but supplied as files that you download, Touchstone files, almost exclusively. We can also say that if we were to have S parameters for a test fixture and S parameters for a device under test and S parameters for the test fixture on the other side, we could measure the test fixture and then determine the performance of the DUT in the middle. We call that de-embedding. We can de-embed the performance of the DUT having measured something bigger. Or alternatively, we could say, oh, I know I've measured the performance of my DUT, I know that. I can embed it with other amplifiers to see how the system would operate. So embedding and de-embedding. Now, when you do this, you have to do everything in one characteristic impedance for your entire system, and generally this is 50 ohm. It does happen quite often that it's say 100 ohm or 75 ohm, but you work in a fixed Z0, as we call it. The characteristic impedance, typically 50 ohms, and your VNA is a Z0 equals 50 ohm product. It is not suitable directly for measuring 75 ohm and 100 ohm systems, although I'll show you how that can be done a little bit later. Okay, so then RF and microwave and gigabit data engineers can compare S parameters of various components and select the ones that they like, either by inspection, or maybe they put them into a simulator and simulate their entire system first. And therein lies the importance of measuring S parameters. You free up engineers, design people to have the ability to do that, to analyze system performance. Right, so an S parameter data set looks like this, or in one form, just one form. There's generally some header information. The plings are like REM statements, if you like, or whatever it is nowadays. The plings are user comments, so the user can use these fields to do as they wish. This is a compulsory and defining header line for a Touchstone file. Come to the meaning of all that in a minute. And you can see I've put in, as many people do, another pling line there with frequency, S11 magnitude, S11 angle, S21 magnitude, S21 angle as headers to the columns. And then once you have that data, our network analyzer, as you're going to see, can plot all these graphs. This is linear magnitude, this one's log magnitude, these are polar plots, they're all defined from that data. So in the what's that thing called? Hash. Thank you. Hashtag. In the hashtag line, megahertz is the frequency multiplier. So it tells you that this data is in megahertz or gigahertz or terahertz or on and on upwards. So that's the multiplier. It tells you that this data set is of S parameters. It could equally be admittance parameters or transmission parameters. There are all sorts of, or impedance parameters. There are all sorts of alternative forms for the same data. We shall be dealing with S parameters exclusively. MA, magnitude and angle. That tells you that if you didn't have that line, which is not compulsory, that tells you that the data comes in the form of magnitude, angle, magnitude, angle. The other forms that you can get are dB, which is log magnitude and angle, or RI, real and imaginary. And then this is a R50, nominal system impedance Z0 equals 50 ohms for this data set. The data set need not be 50 ohms, it can be 75 ohms of course, but it can also be a complex impedance, not from a VNA it can't, or not from our VNA it can't, but it could be. So the file format can deal with complex impedance here as well. And one of the questions that you'll get in any demo, I should think, is does it save Touchstone? Does it load Touchstone? And yes, it does. You couldn't really be a VNA if you didn't, to be honest. So, armed with the knowledge of S parameters, does that arm you with the knowledge of S parameters?
Yeah.
Got it? Yeah?
And when the VNA 106 saves an S parameter file, or Touchstone file rather, can you choose whether it's magnitude or is that fixed per the...
It's real and imaginary at this point. That one of our software enhancement requests is that you can change it. But when it saves and when you load, it's real and imaginary.
Right, and there are utilities around to
oh yes, yeah. Yes, to read and convert and all that, yeah. Right. So let's just return. I've just put this back up just as a little reminder. This is our quad receiver architecture with INQ receivers, 4 of them, measuring the ports, forward and reverse on each port. This is the A wave on port 1, B wave on port 1, B wave on port 2, A wave on port 2. Now, I've overlaid some complex maths. This is the only maths you'll see. But we had this diagram in part 1, and I just refreshed it in at the beginning of part 2 here. What I've done is just put onto here the maths behind each of those plots. We don't need to remember this. All we need to remember is that all of the plots are mathematical derivations from the A wave and the B wave. But it just shows you what they are. Magnitude, log magnitude, this is angle, this is rate of change of angle, this is a fast Fourier transform, real, imaginary. This is just magnitude of a division. Simple, but remember they're vectors, vector maths. These are the transmission parameters at the top, reflection parameters at the bottom. Slightly complicated one. We saw that SWR is Vmax over Vmin in a line. What that pans out to be is 1 plus the magnitude of B1 over A1, 1 minus the magnitude over 1 minus the magnitude of B1 over A1. But again, simple maths derivation from the S parameter. Right, so our product. And we define for the product a demonstration kit. It is only ever so slightly different from what the customer gets. But this is a picture of the complete demo kit. The dark blue items are compulsory items that the customer will always get when they order a product. The light blue ones are options that they may or may not have ordered, and the orange ones are demo kit only. So what I show here, this is how it arrives. It arrives in a very nice. Chris Lowe has introduced for me a very nice new case for the product. Don't have one in here with me, which was a bit of a mistake, but there you go. Very nice case. There's the product. Here's the cal kit. Power supply with all the adapters. Fixed wrenches go in here. We didn't have them for the photograph, so sorry about that. But fixed wrenches go in there. If they've ordered them, we get torque wrenches. We'll talk all about torque wrenches and their importance a little bit later. The USB lead is underneath the product. The application software, my beautiful assistant, get off. The application software comes on that stick. There is also a USB stick within the calibration kit, which we'll come to. There's a couple of items up here that are demonstration kit only. There are two low-pass filters. One, the thin one, the long thin one, I'm going to call my brick wall demo filter. It's as sharp as you like and kills frequencies above a gigahertz, something rotten. And then the fatter one is a much more gentle low group delay filter, and we'll see the importance of having the two to enable you to demonstrate the product. So you get those, the customer doesn't get those. You also get a hard copy printout of the calibration certificate, and again we'll see a slide on these. But the importance of this is, the reason I've included it is that the VNA is quite conservatively specified, and I guarantee that. So you can see by reviewing your own certificate for your own demo kit, you can see how conservatively specified it really is, and the customer can see that as well. There's lots and lots of margin between spec and actual performance. Hence it was worth printing it out. The calibration certificate is, by the way, a chargeable option for the product, so the customer can order a CalCert. It has a certificate of conformity to calibration, and it has a full set of data results and plots. And there's a picture of the, I didn't mention the test leads and the USB stick sitting, the USB cable sitting underneath the product. So straight away to the certificate slide. The first page of the certificate, you don't need to see this in detail, but the first page of the certificate is the certificate itself, saying that the product conforms to specification. There is then a table of fairly simplistic functional tests that are performed on the product, and one or two important measurements that are performed. Not a great many, because testing a VNA in isolation as an instrument is not a very demanding calibration. What's demanding is the calibration of the standards. And then, having used the standards to calibrate the product, what performance do you get? And what you get is graphs like this of what's called a BT line. We're going to measure a very, very challenging piece of workload. So having calibrated the product, we measure a very challenging piece of workload. And these plots, at the top of each plot, there are 4 plots, one for S11, S22, S21, S12. Yeah, 4 plots. So and at the top of the plot, we have, in fact, there are 2 lines there. This is the magnitude of S11, and this is the phase of S11 for this particular DUT. And you can see it's made up of a line with crosses behind it. The line is the measurement, and the cross is what the National Physics Laboratory thought was the DUT was. So we are making a comparison with a traceably calibrated BT line DUT. And you can see that the crosses and the line overlay so considerably that you can barely see the crosses on these certificates. At the bottom, there are 2 difference traces. So the blue one is the difference between the crosses and the blue line at the top. And the orange, likewise, the difference between the orange and its crosses. So they are delta plots. And it is those that must meet specification, and you can just see the black lines here. One of them is the black line for magnitude and the other for phase. And so you can see immediately that the VNA is meeting specification by very significant margin indeed when it is measured in this way. Right. So I need to tell you just briefly what a BT line is. If it were a piece of strip line on a PCB, 50 ohm strip line is a certain thickness as it goes along the VNA, along the board, PCB. This is all calculated and very precisely implemented to make a transmission line on a board. And if you want to make a lower impedance line, you fatten it up. So a BT line is a section of, say, 25 ohms in a longer section of 50 ohms. And this represents a very, very bad mismatch. So what we're going to try and do is measure the line impedance, 50 ohm, 25 ohm, and 50 ohm. We're going to try and find the S parameters of that, which is particularly nasty because it's going to be reflecting a horrible level of reflection off the 25 ohms. That's what a BT line is. Now, we can't use a piece of board because it wouldn't be stable enough or anywhere near stable enough for the measurement relative to the national lab. So what we have to do is, this is called a mismatch line. It's a precision engineered piece of pipe, or 2 pieces of pipe, and you assemble it between your connectors. So if you like, this is the outer screen. If I can, or is that the outer screen? Oh no, the inner is in there. There's the inner in the plastic tube. Here's the outer, which has the SMA connectors on it, but no core. It's just a metal pipe with SMA or PC 3.5 connectors on it, yeah? And what we're going to do is we're going to put our centerpiece between our connectors, and we're then going to thread it through the tube and put the tube in as well. And so we're going to have a center conductor completely and utterly supported by the connectors at the end in an air dielectric. Yeah, a very precisely engineered piece of pipe. They're about $2,000 and they come in mahogany boxes with padlocks on the front, that sort of thing. Right. So we're going to now prepare for our demonstration. Let's first talk about the things we can measure, and we need to talk about them in the form of an insertable DUT or a non-insertable DUT. So the insertable DUT is, and my example being the connector or the filter, one of the filters we provide, has a female connector at one end and a male connector at the other. And what we mean by insertable is that a cable that was connected can be broken and the device can be inserted directly. In other words, reference plane to reference plane can be connected, broken, and inserted. So that's an insertable DUT. And you can see that to match up to it, we have a male test lead, male port, and a female port. This is the recommended configuration of test leads for the product that we advise. That's if you want to make all the measurements that the product is capable of measuring, and you want to do it with equal weighting, as it were. But some people will not buy those leads. They will choose to buy 2 males or 2 females because their focus is a different type of measurement. The non-insertable, an example being here a piece of cable. You can see here I cannot connect the test leads that would have to be used to measure the cable, the DUT. And likewise, the amplifier here, it's got 2 female ports. I cannot connect the test leads that are required to test it. The non-insertable device. And then we have finally the single port DUT, and of course we can have either port on that DUT, we would use a single test lead on port 1 to measure that device. We don't need the second port on the VNA if we're measuring a single port device. Now, with the test leads that you're provided with, or that you may have bought as a customer, if you wanted to measure a non-insertable device, you would have to use what's called a port adapter, which we also provide. So you could put a male to male on there, and you would end up with a male test port and a male test port. Yeah? A port adapter. And the beauty of the lead recommendation that we make is you only ever need to use 1 port adapter. You want to keep that to a minimum if you possibly can. When you demonstrate the product, some of the customers will be watching with a critical eye to see how much a Pico demonstrator understands about RF and microwaves and the problems of measuring RF and microwaves. So we want to try and be seen to do things properly and be aware of the things that can corrupt our measurements quite badly. And one that I would like you to be very aware of is this, please. I've said here, be seen to inspect the test lead and the DUT port connections. And these are real pictures that came back to me recently, actually. This is a real picture of an SMA female connector, and maybe you can see there's a complete chunk of gold missing from its inner connector there. That is a badly damaged connector, and we do not want to be seen using damaged test leads. Moreover, we want to be seen to be inspecting our leads so that they can see, the customer can see that we're concerned. Yeah? We're aware that things can go wrong. This is another example. This is a male SMA connector, and on the dielectric, the white dielectric there, you can see lots of particles of gold. These have come about as we've fastened it, unfastened it, fastened it, unfastened it, and there's shavings that have ended up inside the connector, corrupting its performance. We'd want to be cleaning those out, and we wouldn't want to be seen with dirty test leads. So just be aware of that. Quick check of any connectors that we're connecting to, and of course the customer will be asking you to connect to their DUTs, and you don't want to be putting your expensive test leads into rubbish. Or if you do, you probably want to put a connector saver or port adapter in the way first. Yeah. So just be aware that the DUT they give you might be pretty contaminated or broken. Action number 2 when you're interfacing test leads is to make sure that as you're applying the connectors together that they're straight. Don't be tempted to take up an awkward tightening angle. Try and keep the connectors straight as you insert them, such that the threads engage cleanly. Certainly don't try and tighten against a cross thread or anything like that. And when you tighten the nut, you must always rotate the nut. Never rotate the female connector. Now that's quite important, because if you start rotating the female connector, you're rotating a pin in a socket, and they're delicate, and at the very least you can be scraping material off them as you're doing that. So you don't want to be doing that. Now at the very worst, there are some of those connectors, some customer connectors might end up with that pin being screwed into its base. So if you rotate them, you could end up undoing that pin. Fine for you, but the next time somebody inserts, that pin will be too long and it will wreck the connector it goes into. So just be aware, you're rotating the nut, not rotating the female connector. Be seen to use the torque wrenches. So I've provided in the demo kits the torque wrenches because we don't want to be seen not torquing up connectors. Now these two diagrams try and explain why this is so important. They're a little bit crude, but I hope you can get the idea here. This is a female connector. Its thread is going to be on this part here, and then this is its socket inside the connector. This is the male. It's got thread on the inside here, the nut, that spins round freely, and then it's got its pin sitting there. And my arrows are showing 2 important places. The reference plane on the i.e. the end of this connector is the end of this face here. And the reference plane for this connector is that face there. And when you tighten them up, those 2 faces are going to come together absolutely and completely. And if you tighten them up too tight, you'll start to damage those faces such that the connector can go further forward and the reference planes are moving. Yeah, so we mustn't over tighten. When they are tightened properly, those 2 faces are touching, but the pin, it has a shoulder that does not quite touch the socket. You want a gap of about 1/1000th of an inch. What's that in millimeters, anybody? Pretty small. Can't remember in millimeters. 1/1000th of an inch. Pretty damn small gap. And if you tighten too much, we're going to close that gap, and then we're going to move the pin, because it's mounted in plastic or the socket, one or the other. So we don't want to be doing that. Also, if we don't do them up, we might not have them, if we don't do them up tight enough, we might not have them contacting together. So these things, they're remarkably precise, these connectors. The PC 3.5, our premium connector, is particularly a precision engineered part. And we need to respect that and be seen to do things up properly. Next, I'd ask you to load predefined calibration and instrument status. So I said earlier that we don't want to be starting a demonstration with a calibration. So that you can demonstrate a calibration of your DUT, your VNA, your DUT and your test leads, I have prepared calibration, or Paul Bonser has prepared calibration files for your particular instrument and your particular test leads in your demo kit. Now these are not installed with the software, not yet anyway. So I need to ask you, please, to, in each demo kit, please find the Pico TD demo file which lists your serial number. It's a .cal file and it's on the Pico USB stick. This file is not installed. Please copy it to Documents Pico Technology PicoVNA 2. So you've installed the software and that folder will have been created. Please transfer the file. There is another one as well called darktheme.cal. You transfer those both at the same time, and then those are now going to be permanently available for you to load at any time. If a demo's gone wrong, you'll get back to a known working state. Yeah? And you can get to a known working state very quickly when you begin your demo.
What if they want to see a demo of calibration?
Sorry?
What if they want to see a calibration?
You're going to see one later, sir. But it's always, I mean, obviously, if they insist, you're going to do it now. But it's better not to, because it's a lengthy process, and you want to be starting talking about features and benefits rather than calibration. So we do as the customer asks, but in general, they're going to want to see the thing operating first and foremost. You do not want to be doing a calibration. Not least because you might feel under pressure to get it done fast, and that's the worst thing that can happen to a calibration. Both of those files support a wide range of insertable measurements, including time domain for your specific instrument and test leads. This will be reasonably accurate whilst the instrument warms up. You do not want to be calibrating an instrument that is cold. So if you came into the room and calibrated it straight away, it's going to be off before you've got going. Yeah? So a demonstration first is usually the best thing to do. I've chosen 512 trace points, usable down to 50 Hz resolution bandwidth. All of these things we'll explain in a little while. And it starts up with what's about 12 megahertz to 6 gigahertz. And it's running there. That's if you open the dark theme demo and connect the DUT, don't know whether you can see that, but on the screen there we've got an update in trace, and that is giving us a reasonably accurate measurement of that DUT straight away. Right. So we can see a little demo here of how to do that. So file, load, cal and status. So having started the software, I'm choosing one of those two files and I'm starting the sweep there. So I'm up and running straight away. I think it's going to choose the other one. Dark theme, open. So if you want, you can use this. It's exactly the same setup. It's the dark theme. The reason I've included this is better if you're demonstrating to an audience, if you're demonstrating on a screen in bright lights, if you're demonstrating at an exhibition, then I think dark theme works better. Up to you, of course. You can use the light theme or dark theme as you wish. Now, with a VNA, it's a little bit different. User settings are a little bit different from. So what I've done is saved a status of the instrument, a set of user settings, and a calibration. And that's because a set of user settings cannot really be divorced from a calibration. A set of user settings matches the instrument, the test leads, and everything that you had at the time, and we've just recalled a fixed state for the instrument. It includes calibration data. Right, now you'll all have your own way of demonstrating, so I'm not trying to be prescriptive here, but I'm going to now demonstrate one or two features of the instrument and the software in a sequence that I think works. You don't have to stick to the sequence, of course. But what I like to go through first is the main controls. So let's start this little video here. So here I'm using the mouse to drag this sensitivity parameter here. This is the sensitivity of S11 log magnitude. I'm now going to use it to drag this reference point. This is like a positional shift on a scope. I'm now going to use the mouse to drag that reference value, and I can do that on each of these parameters. They're set. You can change those via menus as well, but that's really the way to do it. The touch does work here, but I'm not really promoting touch just yet. There's a little bit of optimization we need to do, picking up the individual parameters and the markers. So I'm now turning on the markers. Here they come, and you can see readouts have appeared immediately on the right hand side, and I'm just showing here that you can pick up a marker and drag it to whatever position you want on the screen. Now, picking up a marker with touch is a little bit tricky right now, but in essence this all works under touch control, touch screen control as well. Okay, so just a quick run through around the controls, because those controls are not obvious. If you don't know, if you haven't learned that, then you'd have to be modifying them directly under the menus, and that's obviously a lot slower to do. You can if you wish, but that is a lot slower to do. Channel and plot flexibility. So the whole thing starts up like this with log magnitude plots of S11, S21, S12 and S22, but as you've seen already, we can plot a load of other things as well. So let's give that one a little spin. So here I've pulled up the display menu. I'm changing the channel 3 to S11 log magnitude. There it is. But this one is a lot more sensitive than the one above. So 10 dB per division, 1 dB per division, the same parameter, two sensitivities, one of the flexibilities you have. What am I doing here? I'm dragging that one to a much more sensitive position. So now I'm looking at this slope, but in high sensitivity. All of the mush has fallen off the bottom. I'm now going to change. What am I going to do next? I don't know. Channel 4, S21, Displaying just 2 of the parameters rather than all 4. Channel 1, linear magnitude, but it's come up as a flat line, and that's because it's got a silly sensitivity on at the moment. So I'm dragging the sensitivity, because linear magnitude plots are basically going to sit between 0 and 1 unless you've got an amplifier. And then I've dragged the reference point here such that I can display linear magnitude. Here again, I started off with a straight line, but I've pulled the sensitivity out, moved the plot using the reference position, so I've got a 1 volt reference rolling off to a signal level of 0 on a linear magnitude plot. What's he going to do now? This is all surprising to me. I haven't looked at this for a long time. Smith chart. So I've changed S11, the plot in channel 1, to a Smith chart. I've changed S21 to a polar plot. A polar plot for S12. And I guess I'm going to do a Smith chart for this one as well, so that everything becomes the relevant polar plot for the type of measurement that is being done. S21 was just in the middle of the circle. All the data was in the middle, but by pulling out the sensitivity of the plot, I can now see the data that was hidden in the middle of the plot. It came up at the wrong sensitivity. Likewise there. Smith charts look okay. Notice I've got live readouts at the bottom here for all of the markers. TD, time domain. So time domain has come up here, look, it's gone off screen. So I'm going to drag it down. Ooh, there we go. I have a time domain plot, the pulse response of the frequency response above. Channel 4 S21 group delay. Here we go. So now what's happened here is I've still got frequency along here, but this is a time axis now. Just going to pull out the sensitivity here. And what this begins to show me here is that delay, initially, can't read the numbers, delay is rising and then falling, and you can see that more or less aligns with the roll-off point of the filter. And as we said earlier, that's differentiated, or the slope of phase change with frequency. So now I think it's going to be 1 channel only. The message has just told me that the 1 channel that's displayed must be the active channel. That's a Smith chart, which we can see all nice and large. So I think probably we're going to have to explain what a Smith chart is now, aren't we? Oh, darn it. Should we take a break? No, all right. Okay, so a Smith chart. We saw a polar plot. We saw a polar plot of S21. We can probably get our heads around the transmission characteristic having a gain vector, a set of complex numbers that represent the gain of the system, the through gain of the system. Well, this is a polar plot of S22. It's just the same plot. as we saw on S21. It's just a polar plot of the real and imaginary components in the numbers that are coming off the processing of the received waves. What's different about it is we put a silly coordinate set behind it, or a graticule. The only thing that has changed is the graticule. We're used to just seeing Cartesian, real and imaginary, but now we've got a whole bunch of circles and arcs on the back of the plot. What on earth do they mean? Let's just check my notes. Okay, now we do not have to remember what everything means on a Smith chart. We really don't. But it's as well to be aware of what the microwave engineer or the person that uses the Smith chart actually sees. Some microwave engineers can tell in an instant such a lot about a microwave component, and the reflection, this is a reflection map of what's happening on that microwave component, and they can see in an instant exactly how that's behaving, and they can calculate or they can see in their mind the Smith plot that they want to see if they've not got the right one, and they can manipulate things to make it look right in a way that I can't do. I really don't have that vision. I only have a partial vision. I don't use the Smith chart a great deal. So we don't need to know a great deal about it, but let me give you this. We've already said that it's the real information and the imaginary information plotted as a polar plot. If everything was matched perfectly, there would be no reflecting signal, and therefore everything would be right slap bang in the center of that polar plot. No signal coming back off the reflection. Yeah? So right in the middle, Z equals 1, match, the match equals 0, no reflection. If we were right over here, we'd have a real magnitude of 1 in phase with the signal that we sent. So we sent a signal and we got the whole lot back in phase. And you might remember that we said that is an open. This is a circle of constant match, and if we are fully out of phase, you may remember we said in part 1, we said that would be a short. The signal went to the end, saw the short, bounced back in antiphase, yeah? So antiphase, this is a big inductor on the end, and this is a big capacitor on the end. All right? This is our low-pass filter still. This is a low-pass filter that we're displaying here. So markers 1 and 2 are in the middle here. It was quite well matched in the middle, and then as we spiral out, increasing mismatch, until we get out to the circle, or nearly to the circle, of total mismatch. So I've drawn some circles and arcs on here, because these all mean things to people that read Smith charts. We've said that the blue circle on the outer is a circle of total match. Can't have data outside the circle, can we? Because if we had data on the outside, that would be more signal coming back than we sent at it in the first place. Well, perhaps we could have that. What would it be?
Reflections. Multiple reflections.
No, it's not multiple reflections. If we had more signal coming out than we sent at it in the first place, it would be a signal source, an oscillator of something that was already connected to another source and was outputting something, yeah? So usually your amplifiers are oscillating if you're outside this circle. So these are circles of constant reflection. No, sorry, I beg your pardon. I said, what did I say? Circles of constant real component. That's not right either. Woo, Mark, what have you done?
Yeah, the constant reflection code.
Yeah. These green ones are arcs of constant. Yes, it is right. It is right. I'm just throwing myself again when trying to read too much at once. Constant real component. These are arcs of constant imaginary component, and this is a circle of constant reflection. So if I had a mismatch of, say, minus 20 dB, then that would be a circle of constant reflection on the chart, somewhat close to the center, because that's quite good match, minus 20 dB. And then we also indicated that we had a big capacitor down here. This whole region is the capacitive region of the plot, and this whole region above the center line is the inductive region of the plot. So you can see we're starting to pick up lots of information about what our DUT is simply by glancing at a chart, if we can read it. Again, we as sellers do not have to know what all the Smith chart means. The customer will know what the Smith chart means. It's just useful to know that it's very useful to the customer. Right, various plots of the demo filter. Let's look at our filter displayed as S11 Smith, S21 log magnitude, S11 log magnitude, and S1 phase. So we haven't got that right now. Let's start the video and get that done. So the Smith chart. Channel 3, S11 as log magnitude, this one's come up as phase. Now phase is all over the place at the moment. The sensitivity was far too high, so we've pulled it down to a sensible level. 45 degrees per division I like using, because it then all fits on. Plus or minus 180 always fits on. We drag it down and we can see that the phase plot swings between minus 180 degrees and nearly plus 180 degrees. This is S11 phase, this is S21 log magnitude. Now, as I drag this marker on here, we can see that the markers on the other plots drag along too, so that we can always relate a point on one of the plots to a point on the other plots. You can also see that I can, and this is unusual for any VNA, I can actually pick up a marker in a polar plot and drag it to a point of interest, and I can see where that marker is on all of the other plots at the same time. So all the markers move together. When I click on a plot, these readings update, and these readings become the measurements from the plot that I just clicked, the active channel, which at the moment is graph 4 S11, and you can see the measurements here are higher resolution than the measurements here. There is more information in this table. So, and I can get that information for any one simply by clicking on a marker in each of the plots. I can change the active channel. I can do that in the menus as well.
Can you program the markers to search for a particular level?
Yes, you can, although I don't deal with it in the training today. But yes, you can you can use the markers to find peak, max, min.
Yeah, and 3 dB.
And 3 dB points, yes.
Tech were making a big point of that in their video.
Oh, were they? Oh, okay. Oh, well, maybe I'll have to add that bit then. Cool. But yes, I didn't address that.
And a reference waveform. Can you put a reference?
Yes, you can. We'll see that used in a little bit. Has it got through that one? Yes, it has, hasn't it? Noise and dynamic range. Right, so we're going to run this one, and it's going to run through some of the things that you can do to make the trace noise more attractive, or to give you more dynamic range. So, on a scope, we have trace average, and so we do on a vector network analyzer as well. We have average, like an oscilloscope, that can average up to 255 acquisitions. It's a trace average. It's not a vector calculation on the basis of lots of S parameter sets. It's a trace average. And you'll see that it works rather like the scope and reduces noise. We have smoothing. Averaging and smoothing, always available right at the top. Smoothing is a rolling average of endpoints, which is a setup thing, through the trace. So that's another way of reducing noise on the trace. Most effective of all is one that actually depresses the noise floor. You can't do that on a scope. You haven't. Oh yes, you can. I beg your pardon. Yes, you can, because on a scope we use a low pass filter, don't we? We can apply a low pass filter and we can push the bandwidth down. Now we're going to do something akin on a VNA, but not the same. So I can apply very low pass filters of 1 kilohertz and 50 hertz, 10 hertz even, and the noise goes right down, as it would on a scope. But of course on a scope, all your information's gone altogether. We're not doing the same thing with this. So I'll demonstrate it in action, but then we'll come back and talk about why it's different from a scope. Right. So I've just stored the traces, all of them, to memory, and I'm going to, Paul, apply data and memory, and you might be able to see a yellow trace has come up in the background. All right, so I stored them to memory, all of them. I could choose individual ones if I wanted. And I'm going to apply average now. I set average, I think it was to 8, something like that, in the enhancement menu. And you can see I've reduced the noise in the trace, rather like it would occur on a scope. I've applied smooth, which has reduced the noise in a different way. And then I've taken average off, and the smooth got a little bit more wobbly. So basically the same. But enhancement, it's on 10 kilohertz bandwidth at the moment. So how come I can see 12 megahertz to 6 gigahertz? All right, we'll come to that. I've just gone up to 140 kilohertz, and the whole thing got faster. That update is now a little bit faster, than it was at 10 kilohertz. And now I'm going down. I've got lots of choices, look. Kilohertz, and oops, it's all slowed down a bit. But still pretty fast, and still as fast as anything on the market. Enhance, and now I'm going to go down to 50 hertz. And if you want to go and get a coffee now, you can see the little marker here is indicating progress through the sweep. So things have really, really slowed down now. Back to 10 kilohertz, because I get bored quickly. Now it's going to end the sweep before it updates, so don't get caught by that if you've been in a slow, deep filter. And remember that it's going to finish the sweep before it updates and kicks back to 10 kilohertz update rate. All right, so the issue there was that we pushed bandwidth down to 10 hertz from a bandwidth of 10 kilohertz, and we're looking at signals at 6 gigahertz, and this is the concept that I think throws oscilloscope people most easily, because this isn't an oscilloscope. This is a frequency domain product, and it has a very, very important part in its architecture: the mixer. The mixer is in the receiver, and when I tune, this is what happens. Let's pan around to the board here. What a mixer does, if I'm tuned to 3 gigahertz, say, I'm actually doing a sweep, aren't I? But if I'm tuned to 3 gigahertz at this instant in time, and I send to the mixer a frequency of 2.999 gigahertz, then my output from the mixer will be at 1 megahertz or thereabouts. And I can do this at all frequencies. So as this 3 gigahertz is doing this, the other frequency tracks the 3 gigahertz at 1 megahertz behind it, and we mix the two together and we get an intermediate frequency that we are processing through this amplifier. So the signal coming out of here is a 1 megahertz or thereabouts waveform, and its amplitude and its phase information are all connected to the original 3 gigahertz. And now I can process this 1 megahertz in fast A to D converters. Well, not that fast actually, 100 megasamples per second. This is an 8-channel scope, if you like. The VNA has fast A to D converters, 2 behind each channel, 100 megasamples per second, and they're capturing relatively short traces, not great big giga thingies that we do, but relatively short traces of data, and so that's an 8-channel scope at the edges there. So when we apply our filter, we do it not to any of these frequencies, but remember, a network analyzer is constantly calculating, say, amplitude of the vector, say, phase. It's constantly updating its network analysis into a measurement of gain or a measurement of phase or other parameters. And we apply the filter to that information, not the RF signal, not the high frequency signal. Clearly, if I applied a 10 hertz filter to 6 gigs, poof, gone, yeah, it's all gone. It's a bit like using the tone control on your radio receiver. Can anybody remember when you had tone controls? Bass and treble on a radio receiver. You know, you're changing the frequency response of the audio. You're not filtering the RF or the IF. Yeah? Now the importance of that is if I select things down to, say, 10 hertz, then I can't see changes that are happening quicker than 10 hertz. So if I was drawing this gain plot is a line, isn't it? And if it had information on it going up and down that was faster than 10 hertz, I wouldn't see it, right? If I went too fast. But if I slow down and I draw it slowly, then I can filter that, can't I? And I won't remove it because the measurement is changing more slowly. And this is why when we put the 10 hertz filter on, the rate of change of the sweep, the source, had to slow down. It slows down to let the filter settle before we make a measurement of gain. Okay, and this is why we can push noise floor down. We could go down to a hertz, we could go down to 0.1 hertz, and some VNAs do go down to a hertz, but of course you'll wait 3 fortnights for the result, and it's inevitable. Nobody can get the data through a 1 hertz filter any quicker than anybody else, right? So it takes a length of time. So that's what we mean by resolution bandwidth on a VNA. It's not quite the same as the bandwidth, the low-pass filter on a scope. It just has the same effect of moving noise floor down, but much, much, much deeper in the case of a VNA, because we can go so slowly. Actually, I suppose on Picoscope you can set 1 hertz filters, can you, in the digital filter? I guess you can.
Run away.
All right, but in essence it's a digital filter rather along the same lines. Okay, happy with that, because that's quite important for scope people. Does that need? Well, think about it, and if it needs me to go a little bit further on that one, I don't want to make things overly complicated, but yes, a VNA or a frequency domain product, a spectrum analyzer is the same. You can have a 1 hertz filter on a spectrum analyzer, and it just makes the frequency much sharper. We must have the same content on the FFTs, mustn't we, I suppose, as the resolution of an FFT changes.
Well, the FFT should increase the sample when they
yeah, which is effectively what the filter's doing, isn't it? Right. Compare 2 filters and group delay. Whoa. Right, so group delay plots time delay for frequencies within the current resolution bandwidth, the group. As the group sweeps a frequency span, it is a measure of the rate of change of phase which our brick wall filter has in abundance. So let's have a look. So on channel 1 I've put the S21 plot of our filter. On channel 3 I've put S21 phase. On channel 2 I've put S21 time domain, and on channel 4 I'm going to put S21. So this is the same parameter, S21, plotted in 4 different ways, including now group delay. And I'm going to have a quick sweep round here, just changing the sensitivity of the plot so that I get a sensible phase response. Now this is with my long thin DUT, the brick wall filter in your demo kit. And this is still using, by the way, the same demo setup as I have provided. Okay, so you've recalled the setup and then you're doing this particular demo. Now what have we got here? We've got the roll-off point, and we can see at the roll-off point phase goes absolutely AWOL, and then we roll off into the noise and phase information becomes indistinct. We saw this the other day, didn't we? We've got a group delay plot that is showing that the slope of phase is changing a lot, and we've got a nanosecond of delay overall. In this particular filter, this is not the same filter as we were using in our unknown DUT. We can see 2 nanoseconds peak there, but we can see we're getting 5 nanoseconds or so, minus 5 nanoseconds or so. In other words, this information, such that it is getting ahead of this information, and it actually does. This is real. It moves forward relative to the. It's not a time machine. It's not magic, but that's what it does. Now what I've done is I've put the fat one in, and the fat one is, you might think it's a rubbish filter. Look, it doesn't go down nearly as far. It's ever such a slow roll off. It's got all sorts of nasty things at high frequency that we might not like. But look at the look at the group delay plot. This has flat group delay. And you may remember the other day I said how important it was that a communication signal going through a filter, you better not change the delay of one part of the modulated signal relative to another part, otherwise the timing the data is all going to be screwed up if you ever see it again, and it'll be corrupt even when you do see it again. Okay, so that's why you've got two filters in. You can also use the two filters together. You can do a really deep noise floor demo using the two filters. I'll show you another way of doing it, but you can use the two together to do noise floor. Applying test limits to data. Oh, a change. I've called up the black plot here. No particular reason. I just got bored with the other theme, I guess. Now, and this is the demonstration filter again, the sharp brick wall one. I've put into your demo some limits for the dark filter. Sorry, for the dark filter. Oh my God. Some limits for the brick wall filter. Now, they're not specification limits, so I cannot guarantee that every one of your filters will meet the limits, okay? So don't worry if it doesn't meet the limits, all the better in fact, because then you'll see the alarm. So you'll be proving that the limits test function works, right? But probably before you wanted to. But you'll see in this video how the limits are. So the noise you're seeing at the bottom is coming up to a maximum. It's peak noise, not peak to peak noise. You don't see the minimum as such on the log scale. So when we see trace noise, we're going to be about 3 times bigger. The peaks are going to be about 3 times bigger than the spec. Okay, so do be careful. You're not going to see necessarily this very low level as a, you know, when you look at it peak wise, you're going to see more. Same with the noise floor, minus 118 dB RMS. When you look at it, it's going to be down at, say, well, it's only probably going to get down to minus 105, because 3 times difference is 10 dB. So minus 118 dB RMS is minus 108, sorry I said 105, is minus 108 dB peak. All right, so let's have a look at that. Oh yes, and just a reminder here, this noise floor, 118 dB RMS typical, that's in the bandwidth 1 megahertz to 4 gigahertz. We are allowed to go slightly out above 4 gigahertz, and it's at 10 hertz bandwidth. So you have to do this as a rather slow process, which we'll demonstrate. Port power is 3 dBm. In the case of the test I'm going to do here, port power is 3 dBm. So we're going to be looking at minus 115 dBm RMS for our noise floor. That's what the spec says it should be. And that is 400 nanovolts RMS. That's pretty damn small, especially as we're looking at 4 gigahertz signals. We're expecting 3 times RMS noise peaks, so the peaks are going to be falling at around 1.2 microvolts, which translates to minus 105. As you'll see in this demo, we don't quite make it, but then we'll show you how to make it. But let's do this one first. So, enhancement-wise, we're going to go first. We're going to do this trace noise. And we're going to pull that sensitivity right down to 0.01 dBs per division. This is the fact that the calibration was done by me a long time ago. it's the demo cal, and so we see that, but what we're looking at here is noise, and you'll see we'll clear up this later when we do a new cal. And if you were to monitor these results here for a while, you'd see that what I'm doing here is I'm holding the minimum, and so now you're looking for maxima above that minimum. And if you do that, you'll see in the numbers that you are good to less than 0.03 dB peak to peak. And because that's a peak, that's a peak to peak expression. So 6 times down on that is 0.05. Yeah. Okay. So that's where that one comes from. Now, what I'm doing on here is S21. I've lowered the sensitivity to 15 dBs per division. We've generally been looking at 10 or higher sensitivities. I've pushed it right down to 15. I'm now going to increase the level because I'm trying to make a full dynamic range measurement. So I've increased the level to 3 dBm. I've started the sweep. I'm going to enhance now by pulling the bandwidth down to 10 Hertz. Apply that, and things get slow. Now, we were looking for minus 105 here. We're not really quite making it. Not quite. Not far off, but not quite. And the reason is we have not done a 10 Hertz calibration at this level. Oh, I put +6. Oh, yes, my calibration was done at minus 3 dBm. So I've gone up by 6 dB, and I've used interpolation in doing that. I did not recalibrate. It interpolated the result, and you can see I'm not quite there on noise floor. So this demonstration alone would not be adequate to get us right down to the noise floor. I don't know whether you saw it. I won't show it again now, but I did a little, there was a point where the whole trace went up and down like this. Yeah, that was me. I grabbed the test leads and I moved them back and forwards about 20 centimeters. So I was flexing the test leads. The test leads have a loss, and the loss only has certain level of stability. Now, these were the premium test leads. They're really expensive, not by the standards of some, but they are expensive, and they're really good. That doesn't mean that you ever get away. You don't get away from flexing test leads. A large amount causes things to move up and down. There is a little mention later on that as well. Right, now, I'm not going to do it because it takes absolutely ages to do a 10 Hertz calibration at a new level, because each of the calibration sweeps is going to have to be at that very, very slow rate. So but when I do it, and I did do it, then the measurements. What have I got here? Yes, here it is down here. It's a little bit off the screen. This one too long, magnitude S21. Ah, yes, right. Here you are. So S21 log magnitude minus 120. And you can see I'm now down below my minus 105 line all the way across. I go above here. That's allowed because I'm just above 4 gigahertz yeah, I'm out of band of the specification. But you can see noise does not do something horrible and nasty out there. Noise stays down at a very, very low level indeed. So this is how you, if you really want to get down there, you have to do the calibration at 10 Hertz and the right level. Really push the errors down, and then the noise floor does go down to the specified level. These are the trace noise plots. And what are we looking for here? We're looking between the minimum, the yellow trace, the held minimum, and the maximum peak. We're looking for less than 0.03, aren't we? Less than 0.03, and I think we're in on that. Yeah, just about. Just about. Okay, so trace noise and noise floor proven to be in specification if the customer calls you to do it. I put some extra figures down here. We don't specify them, but I thought, well, I'll measure what the floor is at various different bandwidths. Yeah, so you get this best floor at 10 Hertz update rate, but what is the floor if you run at at 10 Hertz bandwidth? If it at a kilohertz, 10 kilohertz, and 140 kilohertz, you can see how the different resolution bandwidths let the noise come up. I think what we'll do is we'll add these to our data sheets, because I think customers don't necessarily want to use 10 Hertz and wait for those results if they can avoid it. Oh, there is, that runs, doesn't it? Right. So I've demonstrated most of the features of the product now, apart from calibration. We can now wholly characterize that DUT. So we finally get to the point where we put our unknown DUT, the black box, and we measure for this particular DUT the reflection off port 1, S11, the transmission from out of port 2 as a result of port 1. We can see that S12, it is identical. It is a reciprocal device. It's a reciprocal device. I know there are some small differences down in the noise floor here, but it is a reciprocal passive device. And S22 is very similar, but it is slightly different. S22 is slightly different. We now know this to be the low pass filter that we thought it was. We've got accurate measurements of its insertion loss, which is very deep indeed and couldn't possibly be seen by our oscilloscope. We know that it's got a little characteristic out here. If you inject something like, what's that, 4 gigahertz or so, it's got a response that pops back. Oh, it's just above 5 gigahertz. Sorry, I put these markers at 5. That's 5, so that's what, 5.3 gigahertz, something like that. So we can see a lot more of our DUT now. And these are just the S parameters plotted as log magnitude. Did anything move? Yeah, so I think you conclude it's a well-behaved steep and deep low-pass filter. To a degree, it's re-entrant around 4.2 gigs. Match is not brilliant, but it's okay, out to a gigahertz. As a general guide, match minus 20 dB is pretty good for most microwave applications. It always depends on what you're doing, and maybe sometimes you need minus 30. You're probably never going to see minus 40. It really doesn't get that good very often. And as we said, the device is reciprocal. Now, as you know, as we've gone along, we can do a lot more. We can look at other responses. We can look at our Smith chart and see how the match moves. We can look at group delay of our DUT. We can look at the time domain response of our DUT. And what we find out when we do all of this, the -3 dB point is about 1.03 gigahertz. Marker 4, the insertion loss, is about -81 dB at 1.9 gigahertz. It's re-entrant at marker 5. S11 match heads rapidly into Smith chart orbit. Here we go as we go down through the loss characteristic. We go out into mismatch. That tells us this filter is reflective. You can get filters that are absorptive. They absorb the power instead of rejecting it. But that's a very special type of filter, and this ain't one of them. It sends it all back. The pulse plot shows us the now familiar 2 nanoseconds delay. Here's 0 nanoseconds to 10 nanoseconds on our time base. It's a scope plot, isn't it? It's a scope plot not of a pulse, but of a pulse response to a perfect pulse. Yeah? But it's a pulse response. It shows us the 2 nanosecond delay that we saw on our scope. We've got response characteristic here. We can see in the group delay the 2 nanosecond that we expect to see for the vast majority of the frequencies going through this filter. And then we can see that as it rolls off, some of the signals down the slope get delayed further by 4 nanoseconds.
The time domain response, that is S21 time domain.
It is S21 time domain. These are all, that's time sorry, that's S21, that's S21, that's S21, this one's S11 at the moment.
So, does it make sense then, if you've only got access to one end of the device, to do an S11 time domain?
Yes, you can. It does make sense if you're trying to find, say, distance to fault or whatever.
Yeah.
And we did that. Well, no, we didn't. We did it with the 9311, didn't we? We saw a time domain response for S11, and yes, you can do it to S11, and you will get what was it? It was a straight line, and then it went ding, and then settled out, didn't it? Yeah, you'd get that. It does make sense. Yes.
Yeah. It was S11 that we were getting in trouble with.
You can only have one time domain channel at a time, so you can't do them all at once. You'd have to do channel by channel if you're going through them. And I thought, well, I'm a real devil for doing this. I thought, hang on a minute then. How good is the match between what the 9311 thought of this and what we think of this setup? And so you would be able to change them for your particular filter. All right, so when I use the limits button in the bottom right hand corner, I get limits for each of the display channels: 1, 2, 3 and 4. Paul. Thank you, Paul. You challenged me earlier for not telling you which was which channel, and quite rightly too. And then each one has a start frequency, a stop frequency, an upper limit and a lower limit. And these are the limits that I've put in there. So you can get those displayed fairly quickly. The limits are different for each plot. And you can see I just unscrewed one of the connectors slightly on the output, and the VSWR's gone all out, and the limits test has now functioned, and it's finding a failure against limit test. So this was the idea of the test. You can show that limits test can be applied and how it works, and you simply have to just loosen a connector and you'll see it all move. Which is of course a warning against not tightening connectors properly in the first place. Convenient.
So in the real world, testing filters,
In the real world, testing a filter or a cable or any component, it's simply the case of putting, you calibrate the instrument once, you set the limits up once, you recall the setup, you run the test, and you connect once, measure, pass, fail. It's the same as limits test on a scope. You can use it in just the same way. And the limits, of course, can be applied over to any, they can be applied to any Cartesian plot. We haven't got limits on polar plots. So you have to, that's quite difficult to imagine actually, isn't it? Yes, you can't do that.
What would I do with it?
What will I do?
If it failed? I mean, can it do something?
Well, that would be down to your work instruction in the workplace, wouldn't it? So,
can it ring a bell? Or
Yeah.
Oh, it works. It can ring a sound, and did you see it put a little squiggly marker around where the first limit failure was occurring? So it highlighted it, and it can make a sound. Yes. Or you can read it back over the remote. So over remote control, you can pick up the limits failure as well. Trace noise, noise floor, and dynamic range. Residual error and interpolation errors. Okay, so we specify trace noise as 0.05 dB RMS at the widest bandwidth, i.e. the highest level of noise, 140 kilohertz bandwidth. As with a scope, we would see 6 times RMS as the peak-to-peak noise. So the spec is an RMS spec, but the noise will be seen on the screen as 6 times if it were a scope. Yeah, more or less the same with a VNA. The noise you're going to see at the bottom, it's not peak-to-peak noise, it's peak noise. Yeah, on the VNA. And here you are. This is the screen, the TDT response of the 9311. It was taken at a rise time setting of 100 picoseconds. And you can see what I've done is stretched the VNA and compressed it to align graticule lines, right? So they're scaled and offset to exactly the same, and you can see the match between those two is remarkable. I was gobsmacked, but very, very delighted that 2 completely different ways of measuring this filter agree as closely as that. Yeah, I was close, nicely surprised. Now, the aperture in the frequency domain, that translates to an aperture of 83 picoseconds. So the effective rise time of the VNA, if it had produced a pulse to do the analysis, is 83 picoseconds. So a bit slower than the TDR is capable of, but faster than the default setting that we ship the 9311 with, which is a 100 picosecond default setting.
It makes sense because the 9300 is a 20 gigahertz instrument.
It is, but the pulse isn't.
Yeah, I know, but up there, and this is a 6 gigahertz instrument, so you'd expect it.
The reason the two come out is so. I'd set the thing to 100 picoseconds, which is pretty close to 83. If I'd set it to 50 picoseconds, I would probably see maybe a bit more HF content in this that I couldn't see with the VNA, because my effective rise time on the VNA is 83. But I set them to about the same, actually not intentionally, it was just luck that got me to this position. And yeah, the intercomparison is frankly amazing, I think. So the instruments can be used interchangeably. The TDR 9311 is going to be a little bit quicker in many instances, and it can get a little bit more resolution, but effectively the same. Or to many users, the same. Right, how are we doing for time? Because it's calibration next, we need to do calibration, and then we can choose as to whether we do advanced features and what have you. But calibration, right? So you spent $6,000, but you've bought an instrument that has almost no accuracy at all. It's useless. And I do mean completely useless. It really would be completely useless. And that's because the errors in directional couplers are massive. And we have to calibrate those out. So if you don't calibrate a VNA, you ain't got anything. And this is why we export with the VNA or with the TDR TDT. It's exactly the same. You have to export cal standards with the product such that the user can calibrate his actual setup, his actual test leads, the situation that he's in, even if you're doing really precise measurements. So this applies to a VNA or at any price. Nobody can solve this. It's not a solvable thing. You have to have, a VNA can only make relative measurements. It can't make any absolute measurement. It has to make a measurement that compares with standards. And we supply standards. The standards load through short and open. They're very good, but whatever they are, however good they are, that is not a perfect short, not a perfect open, through, or a perfect load. They all have imperfections. And if we're going to use a VNA to its full accuracy, we're going to have to tell you exactly how bad that is. In other words, we need data sets. Looks like these, but it's actually just a set of numbers on a USB stick. So in the calibration kit, up in the top here, there's a tiny little USB stick. And that has the data for these serial numbered standards, 2 files, one for this one and one for this one. And it has 4 sets of data on it for each of the components embedded in the standard. And each set of data has 200 points, and each of those points is traceably measured by a golden VNA against its cal standards, and its cal standards are calibrated at NPL. So directly traceable back to national standards. Now, we could use standards of any value, actually. You could use 40 ohms and 60 ohms, but then you'd be capable of measuring between 40 and 60 ohms, and you wouldn't be able to go outside that range, right? So that's why we use short through to open. And you could just do that. Not very well. We're really focused on a particular impedance, Z0, the characteristic impedance of the VNA, and all the measurements that we're going to make, 50 ohms. So it's handy just to have a load, essential actually. We need a precision measurement of what precisely 50 ohm looks like. Well, no, not precisely what 50 ohm looks like, but pretty damn close to, provided with a data set that says how close we are. And what we're going to do is we're going to calibrate the VNA, and we're going to make it measure not perfection, but these sets of data for each standard. So don't think that when you connect the load you're going to get a perfect flat line. You ain't, because it's imperfect in a very well-known way. So what you'll get is a plot of it. And likewise, the through is never going to be no loss. If you zoom right in, you put that through in and you zoom right in, you're going to see a curve with something like 0.15 dB of loss, up to 0.15 dB of loss, because that's the loss of the through. Yeah. So known data is what we're providing here. There are various ways actually of calibrating. There are other ways of calibrating. There are all sorts of standards that can be used. Multiple shorts of different lengths, transmission lines of sliding length. You can do all of these things in more advanced VNAs. We do not support those forms of calibration, and neither do most of our competitors, as you'll see in the competitive analysis. We use short, open, load and through. What a difference a calibration makes. Let's load the factory default settings for this instrument, not for these test leads, and not for this instrument. Sorry, I said this instrument. Let's load the factory default settings. They are an average set of settings for all the VNAs. So a nominal set of data. We're going to load that and we're going to see how bad the VNA is, and then we're going to do the calibration, or I'm going to show you what the calibration does to correct things. Right, go. So load cal and status. Here it is. Factory defaults.cal is available and you can load it. I don't suggest you do it very often, and straight away we can see some problems here. We've got responses that are not that are not the ones we saw before. We've got ripples in there. We've got a Smith chart to die in front of. Now this is why you are not going to do any demo that is not calibrated. Just don't. It's just a big no-no, because you'll get that and the customer's going to say, what? So that's not the way to do it. But that is the default cal. That was not the chart of my cal. This is my cal, and you can see that all the ripples have gone. They're not completely eliminated because things will have drifted since I did the cal, or since Paul did the cal on your demo kit. So they're not completely eliminated, but at least you get sensible data. So always use either the demo cal, one that you've prepared for yourselves as well, you can use, but don't do no cal at all, or don't leave the cal that was last used in front of whatever customer, whenever. When you fire up, you're going to get that back. That's going to be the settings at fire up. It's going to be the last used calibration. It might not have been with your test leads. It might not have been done with your standards. So you don't know what you're going to get when you power up. You must load a calibration or perform one. Right, so connectors, adapters, cables that we use are all going to contribute significant errors in their own right. The precise test setup through to the reference planes, remember we were putting reference plane markers on all of these things earlier, that precise setup must be included in the calibration. VNA calibration is therefore a regular process dependent upon required accuracy. It can be typically daily or hourly, or at every change setup and location. That's what affects salespeople. This is what affects people working routinely in the factory. How accurate are their measurements? Maybe every hourly. Maybe their work instruction is you check your connectors and cables on this sort of repetition rate. But that's only for really high precision work. Certainly daily would be more common. Performed by the user at the measurement point, not in the cal lab. In other words, the user owns and applies the calibration standards. The physical point at which he or she does that are called the reference planes. To calibrate a male test port, i.e. for a female DUT, we will need a female calibration standard. So the standard that you need matches the DUT not the test cable. To calibrate a female test port, a male DUT will be needed. A male calibration standard. Once a calibration has been performed, we want accuracy to be maintained whilst we make our measurements. Three important things can screw things up here. How repeatable will the connectors be when we make and break them? So we've calibrated, i.e. Paul calibrated, and now things have been disconnected and you're reconnecting them. How accurate will things be? How stable will the loss and velocity of the cable be? Well, it is temperature dependent. Velocity of a cable, the speed at which the signal goes along it, i.e. the delay, i.e. the phase, is dependent on temperature. How stable will the loss and velocity be on the cable when we move things about? How stable will the instrument be with time and temperature? So there's a whole bunch of things to worry about. Now what I've asked everybody to do here is to regularly check your cables and standards for damage and wear. We saw a slide earlier where we looked for connector damage. But I suggest you do all this as well, every now and again, in the office perhaps. Connect the ports together and torque all of the connections. View S21 log magnitude and phase at a high sensitivity and store the reading. This is what I've done here. Log magnitude, yellow trace. I stored it. I've zoomed into 0.05 dBs per division and I've stored the trace. Flex the cables over 20 centimeters, allowing the trace to settle at two extremes. So when you do that, the trace bounces up and down, but it will settle to a new position. And here you can see down here, I'm showing you what it looks like with the cables here. I've moved the cable from here to here. And this is what happens. That blue trace has moved simply for that, right? Now, we have a spec on this. Standard cables must meet two cables. So it's 2 times 0.1 dB and 2 times 2 degree over the 6 gig sweep. Now it's normally at the end of the 6 gig sweep that things go maximally wrong. Premium cables should do this. And the instrument stability is something of this order of magnitude if you're charging about in extreme temperatures. Now, so just be warned here, that's quite a small movement. That is well within specification for the cable. But if your cable had become damaged, this is the sort of thing that will pick it up. This is the sort of thing you can show the customer just how good your cables are, because believe me, despite their price, they are good. Here's the thing, Pico's standard and premium cables have a highly competitive price performance, and I'm not kidding. 2 times Pico standard cables, plus or minus 0.1 dB and 2 degrees phase, and they are $558 for a pair. Sounds like daylight robbery, but it actually isn't. 2 times premium cables, better on amplitude and better on phase. They're $1,498 for a pair. 2 times Huber and Sooner 526V are the same spec at 6 gigahertz, $5,500 a pair. That's what you're competing with. Our premium cable is as high performance as that 526V. Fair enough, that cable is good to 40 gigahertz. But people use it at lower frequency because it's one of the most stable on the market. I have got another price in here, the Gore cable, their top cable. It's gone off the bottom of my screen, but it is on the slide. 2 times Gore cable, 0.01 dB and 0.9, so it's slightly worse on phase, and that's $5,000 a cable for the best Gore cable. Your premium cable, it is actually from Huber and Sooner, is as good. And look at the price. And the other cable much cheaper, of course, and only a small compromise in specification. I've looked at a lot of low-cost VNA cables, and boy, I've seen some rubbish. Connectors and cables, PC 3.5 connectors and the slightly faster K-type are air dielectric. You see these pictures down here? This is an SMA. It's got a white plastic dielectric, whereas this is a PC 3.5 pair, male and female. You can see that the landing plane here is much larger than in the SMA. Because the dielectric's there, to keep the impedance the same, they've had to use an outer that's much thinner. So it's much more easily damaged when you torque and over torque. This is a much more precisely engineered plane of a much greater dimension and an air dielectric. Don't be taken in by the fact that these are stainless steel SMA connectors. That's what you get on the end of your standard test lead. These are more common. These are gold ones, gold over brass, but that's got nothing to do with whether they're SMA connectors or not. What matters is whether they've got this dielectric in, not the colour. Yeah? Stainless steel is harder wearing, can be precision machined more accurately, and the plating quality on these connectors is much higher. So these are much more expensive connectors, and they tend not to wear so easily. We have identified we have evaluated SMAs and PC 3.5s, and actually in terms of performance, very little, if any, difference. But we are not going to try and persuade the market that they should always use SMAs, because the market will kick back something rotten. They will not believe Pico telling them that an SMA can perform to the same level as a PC 3.5, because the average SMA can't. Our SMA is a high performance SMA. Leave it at that. We do not need to try and convince them to always use the SMA. And this slide is about the market has grown used to premium cables and standard cables. Premium cables have been so expensive, $5,000 a piece. Standards have been so expensive that Cal Labs have tended to keep those to themselves for their precision work, and you don't let somebody on the outside in the lab, an engineer, goodness me, marketing person, no, we're not going to let them use our expensive standards. So we have reference standards and reference cables, and the market then uses less good standards and less good cables for marketing and salespeople and engineers that abuse them and damage them and all that sort of nonsense. All you have to do is be trained to use them carefully, right? But we have this idea of the working standard and the working cable, the everyday standard, the everyday cable, and Pico's gone along with that, and we provide the two at two different price points. Now, I've got some early indications from our orders. The run rate of premium accessories. The premium Cal standards are selling at about 1/3 of a standard for every VNA. All right, so it's serious business, because these things are still fairly pricey and certainly significant in value compared to the VNA, right? So these are significant considerations as to what your order value is going to be. We're seeing premium cables are being sold at about 0.4 of a premium cable per VNA. Standard accessories, 0.8 of a Cal standard per VNA. So we're actually selling quite well. We wouldn't have predicted that Pico standards would sell this quite well. I really thought that people perhaps wouldn't trust Pico standards initially, but they are. They're trusting the standards, they're buying the standards, they're happy that the performance, the spec is there, even though the price is different. about 0.8, and standard cables 0.75 per VNA. I've seen about 35% of orders not order a standard or a test cable.
Is that pairs of cable, Martin?
Sorry?
But pairs of cables?
Yes, we would normally expect people to take a pair. They might not. They might take, oh sorry, is that, no, that is a cable per VNA. This is a cable per VNA. About 35% don't take either, but might take one or the other, yeah? So it works, it does work out. I know what you're thinking. It does work. It does work out. We've also had several inquiries for accessories only. I don't think we've sold an accessory only at this point, but that is a possibility, because our cables and CAL standards are highly competitive in a very expensive or high value marketplace. Right.
Before we move on from cables, you mentioned yesterday that VNA's got an innovative design, and that's how we can keep the price very competitive.
Yes.
How are our cables?
Okay, so the premium cable, we're very lucky. Huber and Sooner, whilst they're a Swiss company and they pride themselves on the quality of their cables, but they really hadn't established a very good position in VNA cables. And not too many years ago, they launched their 526 range and they tried to go and clobber Gore, which was a challenge and a half, because Gore have just dominated that marketplace, or Rosenberger or other players such as them. But Gore have dominated it. So Huber and Sooner brought the 526 out. It was more expensive, but arguably they would say higher performance. I'm not going to comment because I haven't measured them both. The 126 that we are using was not announced to the market until recently. We had contacted them about cables and they were coming to me with something completely new. And they have tried to make their 126 a high performance cable, but at lower frequencies. And Gore had not done that, and Rosenberger had not done that. So we've had an opportunity there to provide a high quality cable at a low price. And then the standard cables, it's merely been done by me evaluating a large number of cables from a large number of suppliers, knowing full well from my experience in RF and microwave that price does not mean performance, and that you better buy cables and measure them. And it just so happened that Jibo came in with a cable that they really don't sell as a VNA cable, but its performance is superb. So at a price. So two things really, two cables and two lucky finds really, and it gives us a competitive position. The CAL standards are a little bit different. CAL standards we're also very competitive on, and this is LA being the National Physics Laboratory being creative. They have realized that you can use very low cost standards like the short and the open that we provide with the TDR products, the 9311. Those little brass things, they're very cheap. They're like $5 parts. And if you put a PC 3.5 adapter or an SMA adapter of a precision standard on those, and you glue the two together, you have made a short or an open, an adapter or whatever that can perform at a very high standard in terms of every time you connect it, you're connecting a precision connector to another precision connector. Now they're not such good shorts or opens or throughs, but they are stable, reliably stable. And having done this, they've measured loads of them, and our premium standards are outperforming the vast majority of even expensive standards from our competitors. The key measure is of directivity. And ours are coming out at -50 or thereabouts, which is remarkable. You'd pay an absolute fortune and you get a mahogany box for a standard of that performance. We're finding actually we can do the same with the SMAs, but the same argument goes. I'm not going to try and convince the market that an SMA is as good as a PC 3.5. That's not a battle that Pico wants.
Have we any plans for connector saves at all?
Yes, actually somebody else has asked me that one, and I've introduced port adapters. I hadn't introduced, there's connector savers are used in here, right? And I just haven't put them on the price list, but yes I will. Yes I will, I'll put connector savers on. So these are remarkably good. Now we do actually have a slightly lower performance in our standard cal, not because it's made of SMAs, not because of SMAs actually, but Pico calibrates the premium cal standards up to 1 gigahertz. We use a method that has golden standards that LA own and are measured at NPL. Above 1 gigahertz we use through reflect line comparison. We use an airline to calibrate, and that's their most precise way of doing it relative to the national standard, but that's 2 calibrations per port. Yeah, so expensive to do. On the standard ones we use golden SOLT all the way out to 6 gigahertz. So the standard ones are calibrated, the data set is slightly less accurate, and we're achieving about -40 dB on those cals for directivity, and that still vastly outperforms many of the economy cal kits on most of the economy cal kits on the market, and we're cheaper than even those. Pico standards and their data are usable with all VNAs from any manufacturer, and the opposite is also true. So people can use other cal kits if they wish to.
So we've had a couple of people ask for N-type thoughts.
Right, so that sort of question, there is a FAQ, a frequently asked question on the website. I'm talking to LA about it. I have written the FAQ to say what our position is on the N-type. There are loads and loads of different connectors, and N-types are rather large, and for most of the world, or the Western world, I suppose, they're falling out of favour. They're big and bulky and old. They are, however, very strong in the Eastern world, so they still exist in large numbers. Now, I believe that through the use of adapters, port adapters to N-type, that is probably the way to go, and that we should provide port adapters with data. So I'm talking to LA about that, and NPL.
Port adapters to
PC 3.5 to N with data. So that you would then be able to have an N-type cal kit. I don't really want to establish all the traceability around yet another connector if I can possibly avoid it. And the problem being that I've got the legacy connectors, I've also got emerging connectors. So there are a ton of emerging, much smaller connectors.
I think the issue might be that, of course, Tektronix are supplying their VNA with an N-type.
They do, yes, they do, and of course, third party, you can have, you can get N-type things, N-type cal standards, you can use them. You can buy N-type leads very easily, you can use them. I will evaluate the need for them, the ongoing need. I'm particularly aware of the Asian market having a fairly heavy use still of N connectors. So I may be pushed, but at this point they're not available. As I say, a set of words in the FAQ to talk about this and all the other connectors and the attitude to the other connectors, because many connectors you can't actually achieve any better uncertainty by using cal standards in those connectors, so it's not worth doing. That's not true of N.
And the tech cal process cals to the output of the device. It doesn't have a pair of cables.
Yeah.
They bolt the N-type
Yeah.
salt directly onto the front panel,
Yeah.
and one cable there.
Cheap and cheerful. It's cheating. It's cheating, really. What they're doing there is, first of all, Tech, as you'll see in the competitive analysis, have a fairly bad port match, and you can minimize the errors of the port match by getting right up close to it. So that helps, and you can also take one lead out of it, which is one expense. You can choose to cal hours like that if you like. Yes, we could sell one test lead. Yes, we could sell one standard, and yes, you can cal it like that if you like. But that's not what I want to do in demonstration. And also, people have talked to me about Tech. They've said, yeah, I know that. Because they came onto our stand and they said, are you using averaging? I said, I'm not using averaging. Are you using smoothing? I'm not. And they checked. The customers checked that we weren't doing it. Why? Because they just caught Tech doing exactly the same thing. They caught them using every trick in the book to make traces look good. Yeah, well, we're not doing that. We tell it as it is. We specify as it is. We're proud of how it is. And we don't need to play games like cheating. Right. Now, the calibration. So I'm going to show you now how to do the time domain calibration. You won't, this is exactly the calibration that our friend does for us. Thank you. You've done loads of them, haven't you?
Yeah, they're quite quick.
You get quick after a bit. However, I'm going into a little bit of detail here. This is a fairly lengthy video. This is about 12-15 minutes, something like that. It takes us right through the calibration, and ultimately it allows you guys to reinstate the calibration if you need to, but it also shows you how to do one of any nature. Okay, so we go through some of the variations that you can do. There's scrolling text along the bottom on this one. But I'll try and talk you through it as well. Any VNA calibration will be for the complete test setup. So here is my complete test setup with cables. That's what I'm going to try and measure. These are the calibration standards. I'm picking the standards to match the ports, female to go into the male, or vice versa as it is, and likewise. So the ports are matched to the DUT. The DUT therefore determines the cal kits that you require. Because this is an insertable and we've got the two cables with different, we need both cal kits. A lot of cals just need one cal kit. If you're doing 2 males or 2 females, you only need one cal kit. Right, so I pushed that down to a small size, and now we can see the traces on the screen as well. With care, check or load the calibration kit data to the test port. So at this point, I'm going to assume that the calibration data for those kits is not loaded. It will be once you've done it, and then it's reusable. But here we have to load it. So Cal Kit 1, I'm picking the standard female 03 kit. Kit 2, this was in the tools menu up here. Load Cal Kit 2, by serial number on the device. This is the old Cal Kit that is currently in there. Look, some old number there, so we don't want that. Load Cal Kit. It comes straight. You can of course navigate to the Cal Kit data if it's not where you expect it to be. That comes on the USB stick, or of course once you've transferred it across, it's in your PicoVNA folder. Next thing to do, once you've loaded the cal kits in the right ports, that's very important, do not get them crossed. We select the enhancement menu and select the calibration bandwidth. The bandwidth that you cal at must be the lowest that you're going to use the cal for. So if you think you're going to do a 50 hertz or a 10 hertz measurement, you must cal at 10 hertz. You can go as high as you like, but don't then try and use the cal below those. I could just type in the two frequencies for start and stop, but I'm not going to do that. I'm going to do a TDR cal. So I've hit the TDR options button. I'm going to select a 512 point, and I'm going to select here either the stop frequency or the start frequency that I think is about right. And then I'm going to, that's 6 gigs on the stop. I'm going to calculate, oops, it's come up to 3 gigs. So I calculate these, so it's come up to 3 gigs. Let's double that then, more or less, something like that. 12 megahertz. Calculate range, start frequency too high, it'll be adjusted, okay, done that, and it's come up with 11.2 to 603. It's calculated the range that I will see in my time base, 85 nanoseconds, the approximate rise time, which is, what's that, 89 or something like that, picoseconds. Then I transferred this data into here. So to do time domain, you're going to use that time domain options menu to set up these numbers. You can put them in directly, but really it's best to use the calculation. And I'm going to do an insertable cal. This is a cal for all S parameters. We know we have an insertable device. I've selected that, and I'm now ready to start, and I've pressed the load button. This is my calibration wizard. It says it's highlighted all of these. None of them are grayed out, so I'm going to have to do all 5 stages. Not necessarily the case if I had just chosen S11 cal or S21. I wouldn't have had to do necessarily all of those. But here I'm going to have to. It says match load on ports 1 and 2, so I'm doing that now, and I'm talking up the connectors as I go. Checking carefully, the load is the L in the top corner. We'll have color-coded dots on here yet, but we haven't got that yet. That'll be there soon, I hope. When completely satisfied that we've done this correctly, we're going to hit OK. So I'm just talking up the connector there. This is a spanner in effect. I'm holding the standard, so it isn't rotating. The cable's not rotating. I'm using the torque spanner to do things up. Press OK, and it will do the calibration sweep. There it goes. It's doing the sweep it needs to do. It's reasonably slow because it's a 50 hertz sweep. Done. Highlighted. So now we're going to do the short, and it says put a short circuit on both ports 1 and 2. Short. So always essential to be accurate and check this message before you go hitting anything else. Check you really did do what that says. This instruction changes with different cals. You might have short and open on here, right? So you got to do as you're told, not as you thought you were told. Very important, because the mistake won't get identified. Now the reason it won't get identified is because certain VNA users do very clever things by not using shorts and opens to fiddle things, right? So you can't actually detect that it's doing the wrong thing. So be very careful. And the trouble with getting it wrong is the data that you see on the screen will just send you into a complete spin. You won't know what the data looks like. It's completely unfathomable nonsense on occasion. So you really can be totally misled by making a mistake. So check carefully. Not the process to do in a hurry, which is why I said try to avoid doing calibrations first thing when you've need to get the customer settled and you need to tell them all about the product. You don't want to be talking when you're doing this. Not too much anyway. Oh, if we run out, so am I. so are all of them. So I'm trying to use the best practice here. Spin the nuts, not the connector. Correct torquing. TORQ, not the other one. I'm even putting the calibration pieces in the same position as I'm going to have the dot where possible. You've got to think about this cable flexing. If you're really going to make a really good measurement, you really want those cables in the right place when you're doing this. So I'm pretty close. I'm also refitting the dust caps to protect the cal pieces. We don't want to get contamination in there. We want the customer to see us doing the best practice. So I'd thoroughly recommend putting the dust caps back on as you go to keep them protected. So this is the open cal. We're getting through it, aren't we? We're more than halfway now. The reflection one, short on port 1 and open on port 2. Now, one of them's already correct here. We don't need to move one of the connections. We only need to move, for the isolation cal, we only need to move one of them. Isolation, what we're going to do is we're terminating both ports so that theoretically no signal can get from port 1 to port 2. But it does a little bit. There's always a bit of leakage. So we've got to calibrate that out. We've got to recognise that it's there and calibrate it away, measure it and get rid of it. So that's what the isolation cal is doing. The astute here will notice as well, there's a little tick box here, enhanced isolation. The maths takes a little bit longer, but I've found, and the effect of it is it's only effective below about 1 kilohertz. I just leave that ticked all the time because the amount of time it takes is just negligible, really. So just safer, just to make sure that you've done that. Now here it's saying connect the through, but it's calling it 0 length. This is an insertable. We cannot connect a through. Well, we could if we had one, but we haven't got one. We've only got male to male and female to female. This is a 0 length through. We are literally going to connect the 2 cables together. This is an insertable calibration. The through is perfect, has no loss. It has no data. It's perfect. There it goes. Okay, so now we can press OK. And there it goes. This is the last sweep. Right, now we absolutely must remember to apply the cal.
What's the apply on the left of that then that was there just now?
Yeah.
What?
There was
another, we were getting in a right pickle on this in Rotterdam.
What was the what?
There were 2 applies.
Are there?
Yeah, apply and apply.
Apply and apply cal. And we couldn't figure out which was...
Oops, what's happened there? What? Oh. Apply. Oh, right. Ah, okay. This one here on the left.
Yeah.
This is apply for the sweep conditions. You see the box? This is the sweep and calibration menu. Although it says calibration up there, I know, I've just noticed that. Start frequency, stop frequency, that's for applying the sweep conditions, and we can change those at any time. We can change those having done a calibration, and it will interpolate the data to meet the new sweep conditions if it can. You won't be able to do that if you haven't got the data. If you didn't do that enough sweep width and you ask for this down here, you can't do that. But so you can change the sweep, and that applies the sweep. This one is apply calibration. It's a big step applying the calibration. It's a point at which you're pretty happy that you've done things right here. You are going to get a chance to check things out before you save everything utterly and completely. But yes, so two different applies for two different reasons. Let's check reflection and isolation. So I did there a quick check on the through, and I zoomed right in on the S21 plot, and it was really just a noisy straight line. Perfect, because the through is perfect. If it was a non-insertable cal, it would be a slight ramp down because the through that was fitted is not perfect. Yeah. Likewise here, what I'm doing is checking I'm going to check the short and the open. I'm putting them back on, and I'm just doing a quick check of the cal to make sure it's sensible. You don't have to do this every time, but the first time you do a cal, you want some quick checks to make sure it's kind of sensible. All right, now here you see I've pulled this down, and I've got at high sensitivity. I have got some reflection. It's a short, so I should see a flat line, shouldn't I? No, because it's not a perfect short. Likewise over here, I'm going to pull this down, and I get something that looks pretty good. It's only, we're only talking about 0.16 of a dB. That is not coming back when we thought it should, and that's because it's not a perfect open. All right, so quick checks are to see that you get something sensible. If you did it with a load, you might see -40. That's okay, that's good. If you see -10, that cal didn't work. Yeah, so these are quick checks to make sure that before you go measuring or loading anything. Here's the save. I'm actually now saving this calibration using the menu up here, and I'm going to call this. It's the demo test limits. It's the serial number and the demonstration one. So I've saved that whole calibration and settings now, and I could recall that one instead. Right. So I've reinstated the TD cal, and the TD cal is the most complicated in that it has that extra stage where I use the TD menu. Okay, so yeah, I think that takes about 12 or 15 minutes, something like that, to do the check as well. As you can see, it's not that engaging, right? You really don't want to be doing it first thing if you can avoid it. Whoops. It'll often be necessary to demonstrate the calibration customer, but it makes a time-consuming start, and the unit is not yet warmed. That's a really bad idea. You really do have about 20 minutes. It's not an hour to warm these things up, but about 20 minutes. And you can demonstrate the user interface and make some demo measurements before, and have a nice warm instrument to do your cal if you have to. Always tell the customer that that is what you're going to do, that you're recalling a calibration that you did earlier, or that Paul did earlier, and that you'll do a calibration later on. The non-insertable calibration, there are two options. It requires a known through, and the known through is provided on our cal kit. So we have short, open, load and through. That's a known through. It has data associated with it in the calibration file. However, we also have the option of calibrating with the unknown through. And this is a nicely convenient calibration for the customer. Not every cal kit that they might have has a short, open, load and through, because that cal kit was defined to be calibrated with the unknown through. And also in certain circumstances, the unknown through can be the DUT, because in that calibration we are going to measure the DUT and work out what its errors are and treat it as a through. Yeah? And that can give more accuracy in certain circumstances. So the unknown through calibration, it's a mathematically extremely complicated thing to do. Not every VNA supports it, but we do. So it's an important marketing aspect. The unknown through can be literally anything. If you were testing cables, it could be a cable. If you're testing amplifiers, it could be an amplifier. Yeah? The unknown through is a matter of convenience, especially when you don't have a known through.